Today we're going to talk about the dot product. Oh yeah, I got to record your class too. I usually record second hour, but you're first this week or this day. Yay!
Turn up. Can we interrupt your
I would advise against it. Okay. So this is what's going to happen. We are going to talk about the dot product. We are going to work on our homework, and then we're going to transition to studying for our Friday quiz. Okay. Now you're going to walk out of here with a review that you probably won't start because I want you to like do it tomorrow in preparation for the quiz. Okay. We're going to do some things in here to get ready for it. So the dot product. Technically, there are two ways to multiply vectors, but the second way can only be done in 3 dimensions. Don't worry, non-seniors, we'll get there. If I have 2 vectors in 2 dimensions, then we can take their dot product by doing what I have highlighted here. I'm going to have you write it down and then I'm going to talk about it. Okay, so when we take the dot product, essentially what we're doing, ooh, that's bothering me. Essentially what we're doing is we're taking the horizontal components and multiplying them together. We're taking the vertical components and multiplying them together and adding those 2 products together. Okay, so it's important to note when we do the dot product, we are getting a number, we're getting a scalar, we're not getting a vector. Okay. Why is it called the dot product? Okay, so first of all, we're multiplying, so it's a product. Second of all, there's 2 different ways to multiply vectors. So one, they use a dot, and the other, they use like that crisscross sign. Okay, it's called the cross product, and we'll do that in 3 dimensions in May. Okay, so like it's literally 2 multiplications and add them together. All right, so let's try it. Go ahead and write down these 2 vectors for me, please. Okay, so when we take v dot w, we are going to first take the horizontal components, -2 and 4. We're going to multiply those together. Plus, we're going to multiply the vertical components together, 5 and 1. -8 plus 5 equals. Yep, it's just one number. Correct. It's just the numbers. Right? Your turn. You find me this product, dot product. Check in with your neighbor when you have an answer.
-2. What do you mean? I said, hey, Nick, what, actually, no, Nick was telling me what do you got? And I was like, yeah, I also got that.
Yes, okay. All right, Ian, what'd you get? -2. We have 2 times -1 plus 1 times 0. Oof.
So what does that value represent?
Well, it's a scalar that we can do some different things with it. So, like, did you really think that our entire lesson was gonna be this right here?
I was
Okay. Okay, we are gonna do some different things with it, okay? First, let's talk about some properties, okay? You can decide which ones of these you want to write down. Okay, first of all, the dot product is commutative. U dot V is going to be the same as V dot U. Do you believe me?
Yeah.
No.
Let's prove it.
Until
Let's make up some crazy numbers here.
Okay, V. You really want me to?
Yeah. I don't understand it if it doesn't.
No matter what order we have them in, 2 and 3 are going to be multiplied together. Added to 1 and 4 multiplied together. Okay, glad I could help. Yeah.
See, that makes sense.
Okay, if you take the dot product with a vector and the 0 vector, guess what? Your dot product's going to be 0. I know.
no, you don't need to prove that. 3 values now.
Oh,
So the dot product is like multiplication, so it's distributive. If we have U dotted with the sum of 2 vectors, we could distribute it through, and it's the same as U dot V plus U dot W. No, this is pretty much like common sense that we're just putting down on paper. You need to be able to take a dot product. I want to, since we're not working with like number operations, we're working with vector operations. I want to at least have the conversations that, hey, these properties still work. Okay, some properties are going to work and some properties aren't. So we kind of need to talk about that. Okay. Number 4 is actually pretty cool. V dot V is magnitude squared. This one I do want to show you.
yes.
If vector V is A, then V dot V would be A times A plus B times B. Well, A squared plus B squared, well, magnitude is the square root of A squared plus B squared, right? So if we square magnitude, we have the same thing as this right here.
Ooh, that's cool.
Yeah. Yeah. Okay. And then our last property. So C is like a constant, like a scalar. Okay, if we're multiplying a dot product to a scalar, there's still multiplication. We don't distribute into multiplication. We multiply and then we multiply. So you can either do the dot product first, or you can put the scalar with one of your vectors and then do the dot product. But we don't distribute when there's multiplication. We distribute into addition and subtraction. Okay. Most of these, I think number 4 is really the one I want to talk about, but the other 3 I feel like are fairly, or excuse me, 4. The other 4 are fairly, well, I feel like I wouldn't have to talk about them and you'd probably just be okay. Okay, but hey, we had a conversation. So here we go. What can we do with a dot product? Well, you can find the angle in between two non-zero vectors by using this lovely formula right here in red. The angle in between two vectors. So yes, you'll need your calculator in degree mode. And yes, I will give you this equation on the quiz. You're welcome.
Rough test.
Can't remember. Right. So basically what's happening is if we have two vectors, we can take their dot product and divide it by the product of their magnitudes. And the cosine of theta equals that. So we could say the inverse cosine in our calculator of this number right here, and boom, we have our angle in between. Okay. So a little bit of work, but I mean, really not bad. Okay. Now, before we get to an example, I want to talk about parallel vectors. Since we're having this conversation of the angle in between two vectors, what would be the angle in between vectors that are parallel? Okay, we either have vectors that are going in the same direction or vectors that are going in opposite directions.
How would you label that angle?
This angle would be 0. This angle would be 180. If you put them in standard position, these two would form a line. If you put these in standard position, these would be overlapping each other. Okay, so the angle in between parallel vectors is either going to be 0 degrees or 180 degrees. Why am I mentioning this? Well, in your homework, you're going to have some problems that ask you to identify if the vectors are parallel. If one of these two numbers is an answer for you, you have parallel vectors. Should we try our formula? Let's do it. We're going to find the angle between V and W. Ooh, these look awfully familiar. Are these the two from our first example? Okay. I don't know if you need to rewrite them down or not. But here are the two angles I would like to use. Or the two vectors. I don't know. All right, so we need magnitude of each and we need the dot product. Do we have the dot product? What did we figure out the dot product was? -3. Okay, oh, are these different? Okay, I was like, oh, did I not? Okay, now let's talk about the magnitude. Let's talk about the magnitude of V. The magnitude of V. We would have the square root of, what'd you say? 29. Because we have 2 squared plus 5 squared. Here we had 4 squared plus 1 squared. Square root of 17. Okay, so in your calculator, oh, it's taking so long. Okay, in degree mode, I want to talk about something real quick before you go. So second cosine, since we have a fraction and we have a product in the fraction, I would highly encourage you to use this fraction button, the alpha y equals, to make a fraction. That way you don't have to worry about messing up your order of operations. -3 over the square root of 29 times the square root of 17. If you don't use that fraction button, you are going to have to put parentheses around your entire denominator. So if you have a TI 83, that would be my suggestion to you. 97.7 degrees. .77 degrees. Okay. So let's just make sure that that sounds reasonable. Well, let's plot our 2 vectors. I am going to plot V in purple, so -2, 5. And I'm going to plot W in blue, 1, 2, 3, 4, 1. If these are my 2 vectors, would it seem that our angle in between is about 97.77 degrees? Okay, that picture seems to match our answer. If they were like super close together, we might have a problem. Now, this formula will always give us an angle between 0 and 180. So it's always going to go for the closest angle. So technically, like, we have this angle in between vectors and this angle in between vectors. It's always going to give you the closer one. Okay. All right. Vocab time. Orthogonal is something that we need to talk about in terms of our vectors. It has a special meaning. Here, go back. Arrow up. Okay, go to mode. There you go. Okay, braces. What do braces do? Okay. And teeth are straight when they make what kind of angle with your gum? Oh, okay. Orthogonal vectors form a 90-degree angle. I didn't say that. Hold on, I've looked this up before. Ortho means straight or upright. So if you think of like the upright, okay. I don't, dentist.
I assume, yeah.
Straight.
Wow. Okay, so we are going to be able to figure out if we have orthogonal vectors from one piece of information. Okay, so if we have orthogonal vectors, our angle in between is 90 degrees. What is the cosine of 90 degrees? Ooh, 0. So if we have the cosine of theta equals 0, then that means theta is 90 degrees. That's what you're telling me. Oh, which means if our numerator is 0, the entire fraction is 0. So if u dot v is 0, then you know your vectors are orthogonal. If the dot product is 0, you can stop, you know your vectors are orthogonal. If the dot product is not 0, they have a different angle in between that you can find. Alex?
Is there a shortcut of figuring this out without that?
The dot product is your shortcut.
Is there a shortcut for that?
No. The dot product is your shortcut. Okay? What? Oh.
Makes sense, like, that is the
Yeah.
All right, so here are two vectors, 2, -3, and 6, 4. If I ask you, are these orthogonal? Then show me with some work, okay? If I ask you if vectors are orthogonal, then I need to see evidence that you found a dot product and the dot product is 0.
Orthogonals.
No,
Straight line.
no,
Straight.
no,
What's gonal?
upright,
Oh,
upright. Or
Or, wait,
all right, work. Work. Those of you in physics.
Yes.
Work equals force times. In our book, it's distance. Okay, work equals force times distance. Work equals force times displacement. We're gonna find work today. We have one last example, and then you're gonna get to start your homework. Okay, so we're gonna do a problem that I don't want you to have to like write all of it down. So it's actually coming from our book. So you can label that this is the problem from your book. And if you have questions about how you set it up, you can reference that problem in your book, okay? So this is problem number 72 from section 6.4. Okay, this is problem number 72. A tractor pulls a log 800 meters, and the tension in the cable connecting the tractor and the log is 1,600 kilograms. The direction of the force is 35 degrees above the horizontal. Okay, we have a field. In our field, there is a log. This log is connected at a 35-degree angle to a green tractor.
Okay. Okay. These are big old wheels. That's way too small.
Draw like
Expand them.
a little rectangle and then we put.
At least the back ones are
35
huge. Back ones are huge.
It's just a picture. Okay, now,
Looks like a car.
the tension on the cable is 1,600 kilograms. So I'm gonna label this 1,600 kilograms. And we're gonna think of this as a vector with magnitude 1,600 and direction angle 35 degrees. Are you okay? Okay. This is my free body diagram and it's fine.
Yeah, I'm following the force is telling me, why is it in kilograms?
And why is
What
the
are you
timer so
doing?
small?
Because it's math class. Okay. Now, is the log moving at a 35-degree angle?
No.
No, the log is moving along the horizontal. So when we take work equals force times displacement, the force that is happening needs to be the component of the vector in which the direction of the movement is. So since this log is moving horizontal, our force is not 1,600. Our force is 1,600 times the cosine of 35 because that's the horizontal component of our vector. And it said 800 meters. In your calculator, please take for me 1,600 times the cosine of 35 and then take that times 800. I will let you know. Next today. 1,048,514.62. We took meters and we multiplied them by kilograms. A very popular one in math class is foot-pounds. No, foot-pounds, we're multiplying, so there's no slash. Foot-pounds or meter kilogram. I know it's weird, I know it's weird, just push through, okay? It's one day. Okay, so here's what's gonna happen.